You have. It was kind of a rhetorical question. Okay, whether or not you remember it. Okay, you've seen that before. We're going to spend a bunch of time working with, those are called rational exponents in the exponential unit, okay, which is after this one, okay? So what we're going to focus on for right now is an index of 2. So they've kind of labeled all the components of the radical. You've got the index, you've got the radical sign, which is kind of the hook portion, if you will. You've got the radicand, which is underneath, and then the radical as a whole. Okay, the whole thing would be called the radical. And then the radical has the 3 components. Okay? Is everyone okay so far? So there's a whole bunch of stuff that we can do to these around like simplification. And these kind of get a little bit fun, actually, to be honest with you. I kind of like them. Okay, so our focus with radicals will be the index of 2. In other words, it'll be the square root for now. Okay, and the root of x is a positive square root called the principal root of x. Okay. So to simplify radicals, we're going to write the radicand as a product of a perfect square and another factor. Do we know what that means? Not yet. We might with an example. But basically, we're going to take something that is perfectly square rootable, like 36. We can do square root of 36. Everyone agree? And when I multiply these things together, it's almost kind of like x and x. When I multiply them together, I kind of get x squared. It's kind of like that. Okay, I can multiply the radicands together, or the radicals. Okay, so with something, okay, we're going to separate into 2 radicals and then simplify the radicand that is square rootable. Okay, that's a lot of words. Okay, again, I think that typically happens at the beginning of a lesson, but what we'll look at here is the examples will lock it in for you. So, something like 12. So the name of this game is to like write 12 in a product of something that is square rootable times something else. That's, in layman's terms, what's happening here. Does that make sense? So how could we write 12 as a product of 2 things, one of which being square rootable? What 2 numbers? It's almost like you're factoring, right? But with the factor, we're looking for one specific number that we can square root nicely. Owen?
4 and 3.
Okay, 4 and 3 multiply to 12. Everyone agree? Okay, now if I do the square root of 4 multiplied by the square root of 3, that is square root 12. Okay, so I can write square root of 4 multiplied by the square root of 3. What's the square root of 4? 2. So the answer is 2 root 3. How about that? That's kind of fun, isn't it? Have you done this before? No?
I don't know. I feel like I remember something.
You might have seen some of it. It's just simplifying. We call this simplifying, like simplifying radicals. Okay? Okay, what about root 24? 6 and 4? Root 6 times root 4? Okay, typically what you'll do, okay, just look at the way that I've written the first one. I took the thing that was nicely square rooted and I put it first so that when I square root it, I just get a number out. Okay, so just try to do that. So Nick said square root 4 multiplied by root 6. So we would get 2 root 6. Okay, now what? So what's happening here? I talked about this with my grade 10s yesterday. Everything we do is reverting. You're just trying to revert back to like the simplest form of a kind of question, right? And so all we're doing is we're adding in one extra piece to deal with. Okay, and so here we have 5 root 24. We already learned that root 24 was the product of root 4 times root 6. Okay, so what I'm going to do here, I'm going to have 5, and these 2 are multiplied together. That's signifying the multiplication because I don't see anything, no order of operation in between the 2, so all I can presume is that it's multiplication. Okay, so they're multiplied together. 5 times root 4 times root 6. Okay, where we just found out what the root of 24 was. So now I'm going to go 5 times 2 times root 6. I can multiply 5 times 2. That's 10. So we get 10 root 6. How's that? Not bad, I think. I don't know. Okay, what happens if we're good with that, what happens if I multiply two radicals together? You treat these like x times x. What happens when you multiply x times x? What do you get? You get x squareds. Okay, so if we take root 3 and multiply by root 2, we should get root 6. Okay, what happens if you take something like, it's not totally the same thing, but pretty close. I think it helps with the explanation. What if you did something like that? What do? You'd multiply the coefficients together, and then you'd multiply the x's together, right? You'd get something like 4x squared. Everyone agree? So, same thing here. Multiply the numbers together, multiply by the radicals together. So we're going to get 4 times negative 3 is going to be negative 12. RJ, come get the lesson, buddy. Okay, 4 times negative 3 is negative 12. And what's 5? What's the square root of 5 multiplied by the square root of 8? Square root 40. Am I done? Because I think I could simplify the square root of 40. Maybe you can't. There are probably going to be some instances where like you can't. But we know for sure we're going to try and find a nicely square rootable number multiplied by something else. So what are those two numbers, if there are any? Remember, you really have like a couple options, right? We're talking about 1, 4, 9, 16, 25, 36. Ever see what I'm saying? You're looking for one of these, and I wrote them on a diagonal because that would be the diagonal on your multiplication table. Okay? You're looking for one of these in combination with some other number to give you 40. Is there anything that we could write as a product of that to get me root 40? 4 and 10, Ricky? Yeah, 4 and 10. Everyone agree? 4 and 10. Okay, we're gonna get negative 12 root 4 multiplied by root 10, which then turns into negative 12 times 2 times root 10. Right? Are we good? Okay. Let me see. I have an explanation for you. As like kind of an aside, okay? Yeah, you've definitely seen this before, for sure. I know how this is related. I knew there was a reason why I said x times x. Okay. X, what if I had like x squared times x? What do you do? This is a grade 9 concept, which is coming back, right? Because we don't really do that. There's not a lot of exponential work because of how the volume of quadratics in grade 10. So we, like a lot of kids forget about the exponential work, which is totally fine, which is why we go over it again in grade 11. So what do? We have two things. This is called the base, and that's called the exponent. What do we do when the bases match and we're doing some exponent work? What is that answer? Owen?
X cubed.
It's x cubed. Everyone agree? So what's the reasoning behind why it's x cubed? When the bases match and you're multiplying things with the same base, you add the exponents. Agree? So the exponent on there is 1, so that turns into x cubed. That's why I was mentioning the x times x thing earlier. Because now that's going to come back into play. What if I did this? X to the 1/2 multiplied by x to the 1/2. Okay, this is a side. just to prep us here. What's that?
X squared.
Is it x? What's it be x 1/2 plus 1/2, right? Everyone agree? If I add the two exponents, so that's what? It's just x to the power 1, right? So where'd that come from, or why did I bring that up? What's x to the half? We already talked about this today. X to the half is the square root of x. And when I multiply them together, I get x. And it doesn't matter what the number is, right? That's as long as they're... This rule applies when the number, like the radicand is the same. Okay, so let's take a look at this. Typically, when we do these questions, you're not allowed, the first step is to get rid of the radical that's in the denominator. We don't like having radicals in denominators. So, using this, I can get rid of the radical in the denominator. How? Well, if I take this and multiply by root 10 over root 10, what happens? Root 10 times root 10 is what? Just 10. Right? So we get just a 10 in the denominator, which is the point of why we did what we did. But what happens in the numerator? Should get 2 root 300. $30 times 10 is 300. Is that the... That might be the best way to do it. Okay, now, fully simplified. I almost guarantee you could probably do something there. You can for sure, actually. What's another way to write root 300 as a product of two other radicals? Okay, again, we're looking for, ideally, the biggest perfect square rootable number times something else to get me to 300. So what is the, there's one jumping out in my head right now. It might not be jumping out in yours. Owen? 100. 100 times 3 would give you 300, right? So if I could rewrite the numerator like this. 2 times the square root of 100 times the square root of 3, all divided by 10. What's the square root of 100? 10. So we get 2 times 10 times root 3 divided by 10. What happens to the 10s? They cancel each other out. 10 divided by 10 is 1. Right? So you're left with 2 root 3. Now, I find that cool because I would have never, I haven't done this lesson in a while, but I would have never assumed that it was going to condense down into something that nice. Right? Like that's a number. Like if you were to type that in your calculator at the beginning of this question, you'd have 2 times the root of 30, which is going to be some crazy number. And then divide that by root 10, again, is going to be some other crazy number. That crazy number is actually as simple as typing that in your calculator. Do we type that in our calculator and write it, like use it for anything? Like let's say I got that as an answer and I wanted to use it for something in another part of a question. Would I use like some big long decimal? Like I'm trying to get at the heart of what, like why is it we're doing what we're doing? This is an answer. We can use that answer for other things, almost like using it as fractions, right? Well, we're not going to round our answers and then use it in another part of the question. We can actually work with radicals like this. If that's an answer, I can use it just like a fraction somewhere else, and it keeps all those decimals there. Our answers stay exact, right? Where do we see answers like this? Just out of curiosity, you've definitely done this before. Where have we seen the square root come up before?
quadratic formula.
That's right, buddy. There were probably a number of times last year where you were looking at the roots of a quadratic where like you had something that was not necessarily nicely square rootable. And you had, but you did it anyway and wrote down an answer as to what the x-intercept was. What I'm saying is we don't need to do that. If I ask you to do something with that x-intercept now, you can write it as a radical and carry that through the question. Just like a fraction. It keeps all those decimals there. So your answers stay more precise and accurate over the compounding of a question. Okay? What about the next one? You want to get rid of the radicand in the bottom, right? Radicand up at the top. Sophie, if you flip a page, it gives you a breakdown of what everything is. The radical, sorry, I shouldn't have said radicand. Radicand is the number portion. Okay? How do I get rid of the radical in the denominator? That's always your first step. Get rid of like if you see a square root and the radical is just a fancy word for square root, Sophie. Okay? So how do I get rid of the square root in the denominator? You guys kill me today. What's going on? Yeah?
Times square root of 5.
Yeah, just multiply it by the square root of 5 over square root of 5. Are we allowed to do that? What's the square root of 5 divided by the square root of 5? This is 1. So have I changed the question? Because I've multiplied by 1. Right? Okay, what do we get? We get 14 root, what's 15 times 5? 75? 15, 30, 60, 75. Over 7 times 5. Now, what's the biggest perfectly square rootable number that goes into 75? This is maybe emphasizing like your knowledge of your multiplication table. You might want to practice that. Yeah, say 25 and 3. I could write that as, right? So if I take 14 multiplied by the square root of 25 multiplied by the square root of 3, this is almost like your decomposition work from factoring, if you will, right? But except it's multiplication and not addition. Okay, you're trying to take that radical and write it as a product of two other things, one of which being perfectly square rootable. That's kind of the fun game that you get to play now. You know for sure one of those numbers is going to be square rootable. And so you've limited your option to that main diagonal of your multiplication table. And if you can't find one, then it's not, you can't simplify it. Be like not factorable. You just leave it. Okay? So then we're going to have over 35. Okay, so we get 14 multiplied by 5 multiplied by the root of 3 over 35. Now, Mr. Polling's given his class on the next test, and I'm going to do the same for you, just to keep it consistent. This portion of the test will be done without a calculator. Because, for a couple reasons. One, it's not just I'm being mean. I think it's important for you to know that multiplication table, as well as many of you have calculators. This is very fair. Many of you, any of the scientific calculators, you put in like root 75, it won't give you the decimal number. It will give you whatever the simplification is. It will give you 5 root 3. Calculator does the work for you. Okay? So no calculator for this part of the test. Why is that important? I mention that now because I do a lot of the work with the grade 9s in this territory because their first test in the pre-IBs is done without a calculator. So we spend a good month looking at how do I manipulate fractions and adding and subtracting fractions so that I can do this work without a calculator. So there's a little trick here. 5 over 35. What's that reduced to?
7.
7. Everyone no, not 7. 1. 1 over 7.
Oh, wait.
1 over 7. Does everyone agree? 5 over 35 would be 1 over 7, right? And so I get, this is equal to 14 multiplied by 1 multiplied by root 3 over 7. What else do you see now? Again, these questions are like designed in a way for this to work its way out. Right, Sylvie?
It's just 14 times root 3 over 7.
Over 7, but there is one more piece of work that you could do.
Simplify it.
It's just 2, right? So that's what I mean. Like, these questions are gonna be designed from the standpoint where you can do them without a calculator. Okay, where they're gonna work out. So we should get, who would have thought, okay, again, I like this because who would have thought this would have shaken out to be 2 root 3? Well, there you go. Okay. Okay, simplify fully. 2 root 6 multiplied by root 2 is going to go 2 root 12. We've already simplified root 12 today. That's the other thing about this. You're going to start to see common numbers start popping up, like root 12. I know root 12 is root 4 times root 3. So again, the more of these questions you do, the more homework you do, the more style, like different numbers you see, you should start playing the recognition game. Just like, give me two numbers that multiply to 2 and add to 3. That'd be 1 and 2, right? So your factoring stuff, the more factoring questions you do, you start to see conditions pop up more and more often. And then it's not really a thinking game anymore. You're like, oh, I've seen this before. I know what these two factors are. Just like this. Well, I've seen that radical before. I know what that simplifies to. That's the 2 multiplied by the square root of 4 multiplied by the square root of 3. That's 2 times 2 times 3. Well, that's 4 root 3. Okay? Times root 3, yeah. Oh, sorry, babe. You're right. I thought you were criticizing my lack of use of a dot in the bottom line. I was like, oh. Okay, I like these questions. And tomorrow, we go up one more. We mix in addition subtraction with them too. We'll do that tomorrow. Okay? So important you practice tonight because we're just gonna build on this tomorrow. Not tomorrow. I'm not here tomorrow. I don't know what we're gonna do tomorrow. We'll see. Maybe I'll record a video and post it tonight. And then you guys can watch it tomorrow. I don't know. We'll see. And we'll spend Friday taking it up or something. Okay? Okay, 3 times 7. 3 times 7 is 21 root 50. What's root 50? Robbie?
Root 25 and root 2.
Yeah, so we get 21 times root 25 times root 2. So we get 21 times 5 times root 2. What's 21 times 5? 105? That sound right? 20 and 5 makes 100 and then another 5. Okay? No radicals in the denominator. That's your starting point. Okay, that's the starting point for tomorrow too, which we'll discuss later. Okay, you multiply by root 2 multiplied by root 2. Okay, so you're going to get negative 12 root 80 over 4 times 2. Okay, 80 is a new one. I'm thinking about it probably the same way you're thinking about it. Two numbers that multiply to 80, one of which being square rootable. What is the number? I'm still thinking, same way you are. I got one. I don't know. And again, it's not like I think you want the biggest one. The biggest number that is square rootable that divides into 80. And the one that's jumping in my head right now is, Sonia, what do you got? Say that again. Root 16 is a good one. Okay, perfect example. I was going to say root 4 times 20. But the problem with that is the root of 20 is still, you can still simplify that. Okay, so let me, Sonia's right. It's the root of 16 times, what did you say, 8? Was it 8? 5, sorry. Think about this, okay? So I'm going to write, I'm going to write my root 4 times the root of 20. What's great about these, even if you don't identify the biggest one, you're going to see something else that you could probably write as a product of another perfectly square rootable number, right? So that's going to be over 8. Now, what's the problem with what I've written? I could write root 20 as root 4 times root 5. Everyone agree? And then we arrive at the fact that, if I write it again, sorry. Can everybody see that? So there's your root 20, and there's your root 20 again. So you're trying to identify the biggest square rootable number that goes into the number which you're looking for, so that you avoid all this extra work, right? We all appreciate that this is extra work because I didn't identify the largest number. Okay, so from the beginning we could have identified the fact that this would have shaken out to be negative 12 times root 16 times root 5 over 8. Okay, same thing again. Without the calculator, okay, you can reduce 4 over 8. What's 4 over 8? Robbie?
1 over 2.
That's 1 over 2, right? So I could get negative 12. Oop, I missed a square root, sorry. I get negative 12 times 1 times root 5. Sorry, I didn't intend on showing this much work. Over 2. And then negative 12 divided by 2 would be negative 6 times root 5. That's your final answer. Okay? All right. Last question. Try to just get this in here. Okay. Multiply by root 2. That's your first step. Oh, why don't you try this one on your own for a sec? You try to see what you get. Then I'll take it up a sec. Okay. Anybody get an answer yet?
Yeah.
What'd you get?
No, we got the same.
Yeah, it's good for you to work through. Two. Say that again. 2.
2 over 3.
2 over 3.
I don't think so. I don't know.
You're not cooking today, are you?
My
Hey.
water bottle's great.
You're not, buddy. We're taking Sam.
3 times be the square root of 16 over 9 times 4. We get 3 square. We like this question because the square root of 16 is a nice number. It's 3 times 4 over 9 times 4. Now, how many of us would have multiplied the numerator out?
Well, why is it 9 times 4?
9 times 2.
Oh, sorry, 9 times 2. Sorry.
Oh, that is
How many of us would have multiplied this out? So in the interest of the calculator, it's like, hey, when you have to do stuff without calculator, try to keep the numbers as small as you can, right? Because if I multiply 12 over 18, that's not too bad to do. Like I could reduce that a little bit, not bad. But if the numbers start to get larger, then you're going to start to have a bit of a problem trying to reduce it, right? Or it's at least going to take a little bit longer than it would have if you just left the numbers as a product of one another and looked at what was divisible between the numerator and the denominator. That was a very good explanation. I hope some of you were paying attention.
What?
Okay? 4 divided by 2 is 2.
You did. Well, I got the same answer.
And what's the other piece? 4 divided by 2 is 2, and 3 over 9 is what? It's 1 over 3, right? So my answer here would be 2/3. Okay, I'll highlight that because I know I did that, but I'm deliberately making a point, so I'm going to leave it like that because you want to do it like this when you don't have a calculator. Okay? Almost there. Okay, we can also give you questions like this. Okay, so we got steps here. So simplify the radicand, or the radical, okay? Write it as a product of two radicals. And then you could, or should, be able to common factor something out in the numerator and then cancel it with the factor in the denominator, or divide it out. Okay, so root 32. How would I simplify root 32? We're going to get 10 minus a product of 2 radicals. What are the 2 radicals? You always go 1, 4, 9, 16, 25, 36, 49. You're just checking all those, right? What'd you get? 16. 16 times what? 2. Gives me 32. So I can write root 32 as a product of 16 times root 2. And divide that by 2. Okay, so we get 10 minus 8 root, 10 minus 4 root 2 over 2. Now this is like, remember the other day, yesterday, or not yesterday, but Friday I guess it would be, we talked about all the terminology, the coefficients and terms. How many terms are there in the numerator? There's 2 terms. There's a term, there's a term. Last year we discussed this concept, the most basic form of factoring, which was called what? You're looking for things that are common across the terms. What's common across the terms there? A factor of 2. Everyone agree? They're both divisible by 2. So if I remove it, I'm going to get 2 times 5 minus 2 root 2 divided by 2. What happens to the 2's? So our answer,
3 root 2 again.
what do you mean 3 root 2? No, don't do that.
All in.
I don't like that.
But it's 3 root 2. That's bigger.
No, these are not like terms. That'd be like you saying I'm going to combine x and x squareds. Can't do that.
Stop it, Owen.
Okay, just leave that there. That's good. We're good. It's good you said that, on, because I almost guarantee somebody would have written that on their test. Now they shouldn't. Okay, one more. again, you see a radical, and specifically you're looking at the radicand, which is the number underneath the radical, okay? You're looking for a product of two numbers, one of which being the largest square rootable number that you can find that goes into, in this case, 72. So what is that number? You have, like, there are, for a multiplication table of 15, which is pretty significant, that's a lot of radicals that you can simplify. There's only 15 numbers that it could be, right? Sonia? 36 and 2. Everyone agree? 36 times 2 is 72. So if I go -6 plus root 36 times root 2, and you recall, I always write the thing that's square rootable before the thing that is not, so that it doesn't look funny when you, it's like, this looks funny. I hope everybody would agree that that looks funny. Does everyone agree? Okay, write the coefficient. We don't write coefficient, like the same thing here. What's that? I don't like that. I don't like that. You shouldn't like that either. You've never seen that. Write the coefficient out front. You could treat this number as being the kind of coefficient to the radical, right? There's words again. I hope you know words, math words. Okay, so we're gonna get, oh, that's divided by 12 too, sorry. Okay, so we get -6 plus 6 root 2 divided by 12. What's in common? Yeah, or even, I don't like the leading thing being negative either, but I don't think it matters too much. So we can pull out a 6 if you want it. I just don't like that, but it doesn't make a difference. What's 6 over 12? What does that equal to? 6 over 12? It's 1/2, right? So you'd get -1 plus root 2 divided by 2 is your final answer.